So hi guys, this is Dr. Edwards again. Now, let me get started with some basic feature of quantum mechanics. I tend to start here. These are some features, and I want you to play this video over and over again and begin to think about what are wave functions? Why do we need wave functions? And the consequences of them. And this first phraseology here, stationary states wave function. So obviously there must be some other states other than stationary states, because I'm going to focus on stationary states at the moment. But if you're talking about stationary states, then they must be, the wave function must be single valued. If you remember your basic calculus courses, we talked about a function being one-to-one single valued between the independent variables, say it could be the x-axis, and then some function relationship, a mapping between the x-axis and a function that's associated with. So we say the function must be single valued. The function must be continuous. There's no discontinuous places within the range that the function exists. The function is differentiable in the entire range that you're talking about. And the function is square integrable. That means that if you take the square of the wave function and integrate that square wave function over a given range, it must make sense. It must be of some significant value. It must be definable. It can't be infinite, let's say. So those are the those are the features that represent stationary state, a wave function. And the first one I'm going to get to soon will be the infinite square wave in one dimension. Let me go on here. Number two, and this is what I mean here, number two. If you integrate a wave function psi, so this is psi, and this is psi star, which is the complex conjugate of psi. And we'll talk about complex conjugate over and over and over again. Sometimes the wave function, not often, have that imaginary quantity I in it. And the complex conjugate is everywhere if there is an I in the wave function psi, then you change that I to a negative I in psi star, as we call it, which is the complex conjugate of psi. And it must be true then for stationary states. If you integrate over all relevant space where the particle can be, the integral of psi star psi has to be equal to 1. And we will spend a great deal of time trying to figure out how to require psi, how to adjust psi in such a way that when you integrate psi with the product of psi star, the integral is indeed equal to 1. Now this is the Schrodinger equation itself. It is a second order partial differential equation. Don't let that trip you out. But notice that on the left-hand side, it is the imaginary quantity I, h bar. H bar is h divided by 2 pi. It turns out that h over 2 pi occurs so often in quantum mechanics that we just gave it a name. We call it h bar. So the product of I, h bar, and the partial of psi with respect to t, time, of the quantity x and t. So this wave function is a function of time t and a function of the coordinate variable x is equal to, then this first term is going to be the kinetic energy term from classical mechanics, and this second term is going to be the potential energy term from classical mechanics. But the difference is now the kinetic energy term looks a bit odd. It's negative h bar squared over 2m, the second derivative of psi with respect to the x coordinate. And then the potential is the potential energy times the wave function. So solving this Schrodinger equation is the big task that we have in all of our quantum situations. However, there are skill buildings at time that I want you to do certain specific things as we learn how to find psi. In this type quantum problem, stationary states, where the particle can exist in some spatial location. And right now we're going to have it that the particle can exist only along the x-axis. And therefore we want to know what is psi along the x-axis. There's one other odd feature here. The momentum occurs now in quantum to far greater extent than velocity does. And the momentum gets represented in this perverted way in quantum as the momentum along the x-axis is negative I h bar, the partial with respect to x. And this is in that expression there. Okay, let me go on now, okay? All right, that's what I want to say about that. So these are 4 conditions that must be satisfied. Now let me talk about solving the Schrodinger equation in the case of the infinite square wave. The first problem that we get to, it is in David Griffith's book. I need you to go there. And after this presentation, go there. I'm going to start right here in this section, and we're going to talk about this infinite square wave. What is this infinite square wave? It is a region in space where the particle can exist. So the origin is there. X equals 0 is there. And A is in the positive X direction. So the particle can exist in principle between X equals 0 and X equals A. And at X equals 0, the potential is infinite. That's what that arrow indicates. And at X equals A, the potential is infinite. That means the particle is trapped in this region. And that entrapment now leads to some interesting physics. Okay, so now if you, let me change this first. Now, outside the well, as it's called, the wave function is 0. Has to be. The particle can't be outside the well. Has to be on the interior. And so inside the well, though, the Schrodinger equation reduced to this expression. Make sure you can go from what I show you firstly to this expression here. Time is set off to the side. And now, so the wave function is an ordinary differential equation in x. And we want to find this wave function. It turns out that this equation is very similar to the ordinary harmonic oscillator in classical mechanics. The wave function, sorry for this, but this is saying psi can be equal to A times the sine of some kx plus B times the cosine of kx. That this equation will satisfy that one. But now there are some conditions. Because the wave function has to be 0 at x equals to 0, it turns out that we must have here that A is 0. Because the sine of 0 is 1. So for the only way to make this equal to 0 is you must have B equal to 0. Okay? So therefore the wave function becomes then psi of x equals A sine of kx. Now, how can you make this equal to 0 at x equals to lowercase a? Because notice if you put x equals lowercase a, then side a is equal to capital A sine of kx. How can this quantity be 0? It is that ka then can be 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc., etc., etc. Therefore, k takes on specificity. K, we call it in kx, is n pi over a. So therefore now, it turns out that, let me say it here, that the energy of the particle then can be this quantity, h bar squared kn squared over 2m, which equals that quantity, and the wave function now takes on this value here. When you normalize the wave function, you require that the integral of the wave function squared has to be equal to 1. When you do that, you're going to get capital A squared equals 2 pi over 2. 2 pi over lowercase a. So then that becomes the wave function for the infinite square wave. That's it. So now you have learned all that you can know about this particle. You now know that its energy is this quantity and its wave function is that quantity there. It turns out that these are now called orthogonal wave functions, because any one of them, if you multiply it by another and take the complex conjugate, the integral is equal to 0. He shows you that there. What else do I want to know here? He also introduced this Kronecker delta function, that the integral then of psi m star times psi n is equal to Kronecker delta of mn. All right, I'm rushing just a little bit. This is what I wanted you to see. So I finally have introduced you now to this quantity here. I'm going to give you a homework problem then where you will have to show me how you get this expression here. Make sure that you can perform this integral and make sure that the energy of the particle in any value of n, and n equals to, let's see, what's the lowest value of n? N can be 1. That's the lowest value of n here, and that is going to be called the ground state. All right, so we've gotten started then with this concept. That's what I wanted you to do firstly. Now I'm going to give you a homework problem pertaining to this concept. You play this video over and over again until you learn about everything that I'm talking about here. It'll be good for you to even practice to verify that this integral here is equal to 0. Okay? I'm not going to require it, but it's worth your time. All right, young people, that's what I wanted to share with you in this situation. I'm going to provide you some homework problems here soon as I get a chance to put them online. Have a good day.